The objective of this problem is to find the 6 trigonometric functions of this angle in standard position that passes through the point -2, square root of 2. So one thing I would recommend when given problems like this is to first draw a sketch of what that really looks like. And I'm going to add the angle in here. Here is that angle in standard position. But what I'm going to do is really focus on this reference angle because it is part of a triangle that I can draw here in the third quadrant. So let me draw that triangle. Now with this shape, I can start labeling some information on this triangle. Like for instance, this leg is -2. And this leg is square root of 2. And it might be a little strange to think about triangle leg lengths as negative numbers. That's not necessarily the case. What those negatives represent is that this angle has a terminal side in the third quadrant. So that's why I'm keeping these negative values here. What I can now do is use the Pythagorean theorem to get the length of the hypotenuse. So here we have that Pythagorean theorem with the leg lengths included, or I guess, again, though, with the signs that we have. I'm going to square -2. That becomes +4. When I square the square root, those two operations will undo each other. So I end up with +2 equals c squared. So in other words, c squared is 6. Which means c, the hypotenuse, is the square root of 6. So I'm going to add that over here to my figure. Now I have this triangle with the leg lengths labeled, or legs and their signs labeled, to represent that position in the third quadrant, and I also have the hypotenuse labeled. So what I've included over here is a screenshot from page 117 of our text where we are given the definition of the trig functions in terms of the point on the terminal side and the hypotenuse length, or r rather, that's created when we draw out this figure. So I'm going to label those things on our figure here as well. So that means that this -2 is x, this square root of 2 is y, or a y value. Again, if I think of the coordinate itself, -2 is the x coordinate, square root of 2 is the y coordinate. What we found earlier with the Pythagorean theorem is r. Now that we have all these pieces and we know these definitions, we can come over here and start substituting these values. So I'm going to start that process over here. So finishing up that substitution process, this is what I get. So let me move this over a little bit. And at this point, there are some of these that are a little bit simpler than others to simplify. So like for instance, the tangent of the angle, when I have a negative divided by a negative, I could just rewrite that as a positive. And that would be the final answer. And similarly, I could bring this negative in front of the fraction here for secant of theta. The rest of these values have irrational square root kind of answers here, we could say, in our denominator. So we do that process called rationalizing the denominator. To rationalize the denominator, we're going to multiply by a fraction that is the equivalent of 1 in a way that we get a rational number in the denominator. The best way, surefire way to do this is to multiply the denominator by itself. But because this entire fraction needs to be 1, I need to write square root of 6 in the numerator. And because square root of 6 divided by square root of 6 is 1, so essentially I'm multiplying by 1, thus not changing the original value here for sine of theta. I'm just rewriting it in another form. So what we get in the denominator is square root of 6 times square root of 6, which is square root of 36, the square root of 36 being 6. Okay, so notice that immediately now I have this rational number in the denominator. In the numerator, what I have is negative square root of 12. And this you may need to simplify. So you will ask yourself what perfect squares can go evenly into 12 because I can break up my square root that way. And one of those, or well, the only one I can think of here would be 4. 4 times 3 is the same as 12. We can split up that radical like so. The negative square root of 4 times the square root of 3. Notice I'm just taking that negative with me. That was in the original ratio right over here. And then the square root of 4 is 2. So I get negative 2 square root of 3 over 6. And one last thing to simplify is that these two factors here, or these two values share a factor of 2. So I'm going to divide both of those by 2. I'm left with negative square root of 3 over 3. That's the whole process of rationalizing the denominator. This next one's going to go kind of similarly, so I'm going to speed this up so you can see what it becomes. Notice, though, that there was no way to break down square root of 6 into a perfect square times some other number. So all I had to do was simplify the 2 over 6 piece that was in the front. The ones here for cosecant and cotangent, just a little bit different, but the process really is the same. I'm going to pick that denominator, square root of 2, multiply the denominator by that and the numerator. So essentially I'm multiplying by 1. When I multiply these two numbers under the square root, I get 12. When I multiply these two numbers under the square root, I get 4. But the square root of 4 is 2. I'm just bringing that negative with me. Then I have this rational number in the denominator. Square root of 12 is something that will simplify. We did that one earlier. And it's simplified into 2 square root of 3 if we skip over here to this step. And then 2 divided by negative 2 rather, is negative 1 square root 3. This last part is kind of similar, so I'm going to, let me erase that equal sign. I'm going to speed this part up. And when I go through that rationalizing the denominator process and simplify the negative 2 divided by negative 2, I am left with square root of 2.